Welcome to Algebra 1, Unit 8, Lesson 7-2, Solving Systems by Substitution. Pearson Algebra 1, copyright 2009. I'm Mr. Pilarski, and our objective today is I will be able to solve systems of equations by substitution. In a previous lesson, in Unit 8, Lesson 7-1, we learned how to solve systems of equations by graphing. And we found out in that Lesson 7-1 that there were three situations that could occur. The equations could end up crossing at one point, therefore there was one solution, and that one solution was the point at where the two equations crossed. The second situation was where the two lines ended up being the same line. When you graph them, they were graphed right on top of each other, so the equations end up being the same line. Therefore, there was infinitely many solutions because the lines touch in every point. So we can't, since lines continue on without bound, there is infinitely many solutions. The third situation we encountered was the lines ended up being parallel, and since the lines were parallel, they did not cross, and there was no solution. We're going to take a look at today the technique of solving systems of equations by substitution. Because graphing is not always 100% accurate, we have to have other ways to do it, especially if you don't have technology to do the graphing with. So let's take a look here. Solving a system of equations by substitution is best done if one or both of the equations is solved for a variable, such as these two examples. In the first example, we have y is equal to 3x plus 4, and y is equal to 5x minus 8. And in this case, both of the equations are solved for a variable. Both of the equations are already solved for y, so that becomes a very easy substitution situation. But we'll get to that in a second. Let's take a look at the second situation where we have y is equal to 2x and 7x minus y is equal to 15. In this case, only one equation is solved for y, and that would be the equation y is equal to 2x. And I'm going to show you these two examples, and then we're going to look at some individual examples. In this first example here, where we have y is equal to 3x plus 4 and y is equal to 5x minus 8, what happens is, since both variables are equal to y, we can substitute either one of these algebraic expressions on the right in for y. In this case, I'm going to take 3x plus 4, and I'm substituting it in for this y. So the equation I have to solve is 3x plus 4 is equal to 5x minus 8. Now this ends up being an equation with variables on both sides. So what we have to do is eliminate one of the variables from one of the sides. And to be consistent, I usually subtract the variable from the right-hand side. So in this case, I'll subtract 5x from each side. The 5x's on the left cancel each other out. On the left-hand side, we have 3x take away 5x, which gives a negative 2x. Bring down the plus 4, the equal, and the negative 8. Even though this was subtraction, when we eliminate that 5x, it becomes a negative, so we have to bring it down as a negative 8. I continue to solve this equation by subtracting 4 from each side. On the left-hand side, that gives us negative 2x is equal to negative 12. Negative 8 take away 4 is negative 12, and I continue to solve for x by dividing each side of this equation by negative 2, because that's the coefficient of the x. So that gives us x is equal to 6. What we have to do now, remember, a solution is an ordered pair. A solution to a system of equations, if it has one solution, is an ordered pair. So we have to find the y value. So we take this x value and we're going to substitute it in to one of the original equations. And it doesn't matter which one. I'll just choose the first one for this example. Y is equal to 3x plus 4. And we're going to substitute that x, which is 6, into this x here in the equation, and then simplify it to get our value for y. So when I substitute in, that gives 3 times 6 plus 4. Doing the math, we're simplifying the right-hand side. 3 times 6 is 18, and 18 plus 4 is 22. So the two parts to our solution here are x is equal to 6 and y is equal to 22. And ordered pairs always come in the order x comma y, the x coordinate and the y coordinate. So our solution for this problem is 6 comma 22. These two equations sorry about that, wrong number interrupting the video. Anyway, I believe I was talking about 6 comma 22 would be the point where these two equations would cross if we were to graph them. Now if we take a look at this system here, y is equal to 2x and 7x minus y is equal to 15, we notice only one of the equations is solved for y. And that's the first equation, which what that means is we're going to take this 2x and we're going to substitute it in to this y. So we're going to rewrite the second equation, but instead of y, we're going to put in the 2x. So this becomes 7x minus 2x because we took the y out and put in the 2x is equal to 15. This is an equation with variables on one side, and we have to combine these two like terms, 7x minus 2x, which gives 5x. Bring down the equals into 15. Then we solve this equation by dividing each side by 5. So we find out x is equal to 3. Now we have to substitute this x is equal to 3 into one of the original equations, and I think this case, the first equation would be the easiest. So we'll have y is equal to 2x, where we have to take the 3, substitute it in for the x, so we get 2 times 3, so y is equal to 6. Therefore, the solution to this system of equations is 3 comma 6. So let's take a look at example 1t using substitution. This is like the first example I did on the previous slide. Y is equal to 2x plus 2 and y is equal to negative 3x plus 4. We can see that both equations are already solved for y, so what we need to do is simply take this part of the first equation and substitute it into y in the second equation, so that the equation that we need to solve is 2x plus 2 is equal to negative 3x plus 4. This type of substitution gives you an equation with variables on both sides, so we need to collect the variable terms on one side. I'll do that by getting rid of the negative 3x by using the addition property of equality, and I add 3x to both sides. On the right hand side they cancel out, leaving a positive 4. On the left hand side, 2x plus 3x is 5x, and bring down the plus 2. I continue to solve by subtracting 2 from each side by using the subtraction property of equality. 2 minus 2 on the left cancels out, leaving us 5x is equal to 2. And then I divide each side by 5, which gives us x is equal to 0.4. And that's a perfectly legitimate answer. Now we have to take that 4 and substitute it in, or the 0.4, and substitute it into one of the original equations. Again, you could use either of the equations. I'll just use the first one here. Y is equal to 2x plus 2. And we're substituting that 0.4 in for the x. So then when we substitute, y is equal to 2 times 0.4 plus 2. When we simplify the right-hand side, we end up with y is equal to, well, 2 times 0.4 is 0.8, and 0.8 plus 2 is 2.8. So our solution, remember it's in the order x comma y, or the x coordinate then the y coordinate, so our solution here is 0.4, 2.8. So this system has one solution, and this is it, 0.4 and 2.8. If we look at example 2t using substitution, this is where we have one of the equations solved for a variable and it happens to be solved for y. What we're going to do now is we're going to substitute this 2x minus 1 in for this y right here, so that when we do that, the equation that we end up with, we're going to rewrite the second equation, 4x plus 2. Now we're taking out the y and we're going to substitute in the 2x minus 2. I'd like you to notice that I put the 2x minus 1 in parentheses. I believe I said 2x minus 2 before, but it's 2x minus 1. You need to put it in parentheses because what we took out, the y, was a single term, and what we put in is two terms. So we're going to have to remember to, when we solve the equation, distribute this 2. We need to multiply it by both terms of what we substituted in for y. First, I'll bring down the 4x. And to, like I said, first solve this equation, we need to distribute this 2. 2 times 2x gives 4x. And 2 times minus 1 gives minus 2 is equal to 12x. We next combine these two like terms on the same side. So 4x plus 4x gives 8x. Bring down the minus 2 equals to 12. Then I add 2 to both sides. On the left-hand side, the 2's cancel out, leaving 8x. Bring down the equal sign, and that's 14. So 8x is equal to 14. Then I'll divide each side by 8. The 8's on the left divide out. And on the right-hand side, that gives us 14 over 8. But 14 over 8 does reduce. It reduces by a factor of 2. 14 over 8 does reduce to 7 over 4, which also gives the decimal number 1.75. So the x value can be expressed as 7 over 4, 1 3/4, or 1.75. So we take this x value, we substitute it back into one of the original equations. In this case, the first equation is probably going to be the easiest because it's already solved for y. So we take y is equal to 2x minus 1. We substitute that 1.75 in for the x. So that gives us y is equal to 2 times 1.75 minus 1. And when we simplify the math on the right-hand side, 2 times 1.75 is 3.5. And 3.5 take away 1 is 2.5. So we now have our x-coordinate and our y-coordinate. So our solution is 1.75, comma 2.5. So these two equations have a unique solution of 1.75 and 2.5. In example 3t, solving by substitution, I want to show you that both equations don't have to be solved for y necessarily to use the technique that we used in example 1t. If we look at the first equation in this system of equations, negative 5x plus y is equal to a negative 8, that equation is easily solved for y. We can solve this first equation for y by adding 5x to both sides. The 5x's on the left cancel out, leaving us y is equal to 5x minus 8. So now we have an equivalent form of our first equation that's solved for y, and we have our second equation that was already solved for y. So what we do is what we did in example 1t, is we take the second part of the first equation, 5x minus 8, and we'll be substituting it into y in the first equation. So that gives us 5x minus 8 is equal to 3x plus 4. To solve this equation, we subtract 3x from both sides because variables are on opposite sides of the equal sign. The 3x's on the right cancel out, leaving us with 4. On the left-hand side, 5x take away 3x is 2x. Bring down the minus 8. Next, I add 8 to both sides, giving 2x is equal to 12. Then I divide each side by 2 to give the x-coordinate to be 6. So then we take this, remember, this 6 here and we substitute it into one of the original equations. And I'll just take the second equation in this case, since it's already solved for y. Y is equal to 3x plus 4. And I substitute this 6 in for the x. So when I substitute, it gives 3 is equal to, or y is equal to, 3 times 6 plus 4. Finishing this equation, 3 times 6 is 18. And 18 plus 4 is equal to 22. So y is equal to 22. So the ordered pair here is 6, 22. Remember, when solving equations, systems of equations with substitution, you're going to be substituting an algebraic expression in for one of the variables. There are different situations that can arise where you have both equations solved for a variable or one equation solved for a variable. As we saw here in this last example, 3t, you can have one equation solved for a variable, but you can ultimately solve it for so that both equations are solved for a variable, and it becomes a pretty easy problem to deal with. Thanks for watching my video on solving systems of equations with substitution. I'm Mr. Pilarski. Bye-bye.